Good morning, everybody, or afternoon, whatever time it is you're watching this. I'm going to go over the next section, 4.7, logistic growth with you. Let me share my screen. Okay, this is the section that will have to do with the extra credit assignment that I will have posted in a little bit for you. It's a project that just has you watch a video and basically summarize it. And it's a video about the logistic growth curve and how it relates to the coronavirus. All right, so logistic function is either increasing everywhere or decreasing everywhere. So let me give you the two basic graphs here. Let's see, draw. If K is greater than 0, you're going to end up with a graph that looks something like this. And you can probably recognize that there's a inflection point there, right? So basically a logistic graph looks sort of like it's exponential at the beginning where it's concave up, and then it hits the inflection point and turns concave down. And that's if the K value is greater than 0. And when I'm talking about K, I'm talking about this K. And this is the standard form of a logistic function. If K is less than 0, you'll end up with a similar graph, only maybe what you've expected already is that you would have concave down first, and then it would level off to 0, where the inflection point is there. Okay, and basically that's what it says here. So here where it says, let's see, logistic function is approximately exponential for small values of t. So if this is t, right, the horizontal axis, the smaller values of t follow pretty much an exponential graph. But then what happens is it reaches a capacity, right, that it reaches a level where it won't get any bigger. And we use it to model things like particularly population. There's a bunch of examples in Wiley on sales of new product. And of course, the spread of a virus like the coronavirus. It has 3 parameters, so 3 things that will make it look differently on the graph. If you change an L value, that's the numerator. If you change the C value, and also if you change the K value. So we're going to take a look at those 3 parameters and how it would change a logistical graph. So here is the standard form again listed for you here. And here we're going to say, all right, let's let K equal 1. So in this graph right here, K is equal to 1, okay? And then graph P for several values of L. So basically what we're trying to do in this example is figure out what does L control on the graph, right? So each of these, when L is 1, then we figure out what P is, right? So if we make this L value 1 right here, then the P value, of course, is 0, right? And so on. So basically, what the L value is controlling is where the horizontal asymptote is. So let's summarize that. So the parameter L determines the horizontal asymptote. And this is, the horizontal asymptote is where it levels off, right? Or reaches capacity. And this is important, guys. This is where graph levels off. Or reaches capacity. Or another way, like Wiley, for example, could ask you a question is reaches its highest like population. So on your homework, a lot of times when they're asking you for a highest value, like the highest number of sales or the largest, where on the graph does it reach its highest population, it'll be at that horizontal asymptote. Okay. So again, on each of these graphs, what I've done is for this one, I've made L equal 1, this L equal 1, and then determined what P is, right? And each time the P, of course, is the Y value, that would be the horizontal asymptote. So basically the numerator or the L parameter moves it up and down, right? Moves the horizontal asymptote up or down. Let's look at another parameter. So for this one, we're gonna forget about L for a minute and we're gonna just make it equal to 1 and see what happens when we change the, let's see, yeah, when we change what happens to the K value, right? Okay, so basically we've done 3 different graphs here. We've done K is equal to 10. Let's see if I can color code this for you. So here K is large, right? In this graph, K was equal to 10. And then in this one, K was equal to 5. Here, we've got K is equal to 1. And so on. So what we can say as K gets bigger, or you can word it as K gets smaller, but we could say that as K, oops, I don't know where I got that different color. No. So as the K parameter gets bigger, the curve is going to approach the horizontal asymptote sooner. So what happens is K affects how steep the graph is, right? Or the rate of growth. And thinking Wiley terms, like how can they ask you that? You think of it as rate of growth. So if you look at K is equal to 10 here, that's growing way faster than K is equal to 1, right? Because it reaches capacity sooner in time, right? Now, if you look at this value here, let's say some small number. And then if you look over here, t equals a bigger number. And remember, t is time. So the k value, if that changes, then it's going to change the steepness of the graph, and therefore it will change the rate of growth, or how fast it will reach capacity. Let's write that. Here we go. Excuse me 1 minute. Okay, I'm back. Okay, so let's look at some properties of the logistical function. Here is the standard form of a logistical function. So remember that the numerator L here represents the carrying capacity, right, which is the horizontal asymptote. Let's see, what else? Oh, the point of diminishing returns, AKA inflection point, also where the graph changes convexity. So all of those are different ways, like Wiley would ask you for the inflection point, or where's the point of diminishing returns, or where is the graph changing convexity. It all means the same thing, okay? And it occurs at this point right here. You've seen this in a prior example. We were trying to get you ready, I think in the last unit, where something was L, which is, they're talking about a level, and then the point of diminishing returns or inflection point is always going to be whatever the original capacity is divided by 2. And we'll do an example where you'll see that in a moment here. Okay, so let's label some things. So here's the basic function of a logistical function. And of course, this is when k is greater than 0, right? And of course, it's convex down in the beginning when k is less than 0, like I showed you earlier. Okay, so let's see, let's label some of this stuff. This horizontal asymptote is called the carrying capacity. Oops. And let's think of different ways Wiley could ask you a question. Let's say the largest population, an environment, can support. Okay. Another buzzword for questions like this, what's the maximum the population will reach? So there's all kinds of different ways and words they can use, but just know that the largest anything's going to get would be where the horizontal asymptote is. And then to find the inflection point, that would be where whatever the L is, the largest capacity number is, and you just simply divide it by 2. And you'll see there's different kinds of problems, and we'll go over some of those in a minute. But let's label this as the inflection point. Notice that in this graph, I'll use red. This right here is convex, not convex, concave. Did I use the convex word earlier? I did. We'll fix that. Concave up. And then we've got this part of the graph, which is concave down. And I also wanted to point out to you that this part of the graph here is approximately exponential. So a lot of times when we're using a model, it'll look like it's an exponential model, right? I don't know if you guys remember doing regression on your calculators. We're going to do a little bit of that today. But if you put a bunch of values in, let's say from here to here, and put it in your exponential regression, it would look like it fits the model pretty well. But what tends to happen with logistical functions is it looks exponential and then reaches its point of diminishing returns, which is the inflection point, and then slows down a little bit, right? So from here to here, it's going really fast, right? It's exponential, but then it reaches the max and then starts to slow down. So let's, I just want to put kind of all the buzzwords. Look, like if you're confused about a question, go back to these buzzwords. This is the point of diminishing returns. Or capacity, or no, sorry, in this point, it is growing the fastest. Growing the fastest at the inflection point, the point of diminishing returns, because then it slows down after that, but it reaches its capacity for how fast it's growing at the inflection point. And let's see, I said it's another thing I wanted to add. This is approximately exponential for small values, which is the left side of the graph. Okay, so that's all the basics. What else? I did want to tell you something about the C parameter. They don't really go over it here, but there is a question about that on the homework. The C value affects where the curve crosses the vertical axis. The y-axis, right? And one thing that you should know, because they're going to ask you to pick out a graph based on some characteristics, is that the higher the C is, the sooner it's going to get there. The vertical axis. And And okay, I also wanted to fix this. It's concavity, not convexity. There we go. Okay, so let's just do an example. So here's an example, and it's actually a real example. T is in years since 1790, and P is in millions. And here's the data for all of this. We used the following logistic function to model US population. This was the actual model that we used, right? And it says here, according to this function, what's the maximum US population? Well, the maximum US population was in 2010. And 2010, the actual population was 308.7 million people, right? Now, if you look at this graph, the actual data was here, but the logistical function that people in this business used back then was this one. And that actual one here does not fit the data, right? How well does the model fit the growth of the US population since 19? Not well, right? And of course, scientists make mistakes too. Not well. So what do you think happened? Well, it looks like it's fitting. It looks like this approximately logistical graph, right? It looks like this, and you can even see it's logistical. It looks like it's starting to turn a little bit there. Why would it change? Well, if you look at this point in time, this would be about 1940, right? Or 50, around that time. And what happened in the 1950s is there was a 28 million population surge. And if we were really in class, I would ask any of you guys if you recall any sort of population surge around the 1950s. And this was, of course, the baby boom. So it was following the model that the scientists figured out for a long time until the 1950s when there was the baby boom. All right, simple enough, right? Let's go to another example here. All right, here we're talking about total sales of a new product. And like I said in the beginning, when I'm introducing this, population models, sales of a new product, spread of a virus, those are all logistical type situations here. So it says here, when a new application for a mobile device comes out, for example, on the market, sales increase rapidly first, right? And that would follow the logistical early in time. That's the concave up to the inflection point, right? And then, so they increase rapidly, and then eventually most people who want the app have already bought it, right? And sales slow down until they reach a cap or whatever. All right, so here we are going to use our calculators. This should be tricky because I don't have a calculator on my computer anymore since the malware attack in Baltimore County. But I do have a calculator, and I think I can show it to you on the screen. We'll see how that goes. Okay, so first it says find a point where concavity changes in this function. Use it to estimate the maximum potential sales L. All right, so what we're going to do is we're going to look at the change in value here, right? So the change here would be 1.5. And then between these two, we've got 6. The difference here is 25. So it's growing, right? That's the exponential part where it's growing, right? The slope. And here we've got 62 difference. Here it's still growing, 163, until it gets here. And the difference here is just 145. And then here is 93. So the point at which, like they say, the concavity changes, right, is the inflection point here, right? Because here we're going increasing, and then here we start to decrease. Okay, so the inflection point, and that's the same thing as concavity changing, changes when t is 5, and p is equal to 258 million. So what you can say L divided by 2 is equal to 258, because remember, oops, let's write that correctly, because remember, if this is capacity and you've just now figured out what the inflection point is by looking at the data, you know that 258 million is equal to L divided by 2. So then to find L, we're just going to multiply both sides by 2. L must equal 258 times 2, or 532. So L is 532. And we found that by finding the inflection point and then multiplying it by 2. All right, so now we're going to do some logistic regression in your calculator. So we're going to put all the data in and then have the calculator give us what they think, excuse me, the L, the C, and the, what is other parameter, L, C, and K are. Alexa off. Alexa off. That's my Alexa reminding me to feed my dog. Okay, so this is how you do it in your calculator. You're going to hit the stat button. So let's see, let me do that on my calculator to see if you guys can see it. Okay, so if you hit the stat button, let's see, there we go. Here, and the stat button is just below the delete button. You're going to get this screen right here. From there, you're going to hit, right, that is the stat button. Okay, then you're going to pick option 1, which is edit. Okay, and then all I'm going to do, you'll get this screen right here, and you'll just enter all your data in. So notice that, what does it say? Yeah, L1 is all the T's in the table, and L2 is all the P's in the table. So you're just entering all the data, and now we're going to ask the calculator to figure out what the model is for let's say the formula is for this amount of data. So from there, you're going to hit stat again. Then you'll hit the stat button again. And then you're going to cursor over to the right. And this is the calc option. And from there, you're going to scroll down until you find logistic. Now, in your calculator, depends on what model you have. It may not be the B option, but you want the logistic graph. And then you hit enter a bunch of times. Let me think how many. Let's see, once, twice, 3 times, 4 times, 5 times, 6 times. Or however many times in your calculator it takes for it to calculate it. Okay, so what it's going to do is it's going to come up with something like this. And this tells you what all the parameters are. So what it's telling you is for y equals c, this is our L, they're just using different variables, 1 plus a, which is your normal e. Again, we're just using different variables. E to the negative bx, right? Our b is in standard form is actually the k. And then they're telling you what each of those variables are. So if we replace all of those, we can say that we know our C value is 532. I'm just rounding. The C value I got was 531.63, right? That's your numerator. This would be 1 plus, and they tell us that the A value is 869.05, so we'll just say 869. And our B value here, they're telling us is 1.33. So in the formula, there's a negative sign there, 1.33. And here's your X value. Or in a normal function, it would be your T value. All right, and so when you graph it, it looks, you put this in your graphing calculator and it'll look something like this graph. Now let's point out a couple of things here. This point right here is the inflection point, and that is when T is 5, you're going to get 258 sales. So that's the inflection point. And notice too that this is, we found this by just doing L divided by 2. And then we found L up here, which would be where that horizontal asymptote is at 532. Okay, now I'm just going to explain, and I've kind of already done all the notes for you on this next page, but you'll get a couple of questions on dose responses. So here, the curve plots, and here, and this is another really common use of a logistical graph, is doses of a drug given to somebody and how long it stays in the body and all of that. So generally with drugs, you know, the FDA regulates this sort of thing. Here's a logistical graph here, right? And what happens is that a drug is safe and effective in this range, right? In this sort of dose, like levels of dose. So say this is like 0 milligrams and this is like 18 milligrams. So in the doses between say like 5 and 12 milligrams of this drug, it's safe and effective, right? And notice this is a smaller slope than if if this is a steeper slope here, that means that it's getting to its capacity sooner, right? So it's a really steep thing, right? And notice that here, if we go from this point to this point and with a steeper graph, the safe and effective dosage is smaller, right? So you would want a drug with this situation because there's more leeway here than a drug that reaches its capacity sooner. And it basically says this. So here is the broad range of dosages, where it would be broad meaning bigger, right, than over here. And then here, it explains kind of what I just said, but the slope of the curve is steep, and the range of dosages at which the drug is both safe and effective is small. They're talking about this right here. So a small mistake in dosage can have dangerous results. So administration of a drug like this with such a narrow, safe and effective dosage range can be difficult. And finally, this last one, I think this is it. Yeah. So it says, what does the slope of the dose response curve tell us? Well, for both drug A and drug B, notice that this is the maximum safe response, this is the minimum response. So you want to be somewhere in between here, and both A and B are not in between there, right? And drug C is really the only one that is in the safe response within the range here. So again, they say here that both A and B are above the maximum up here. And if you want to look at it, actually drug A reaches this level more quickly, right? Because it has a steeper slope. And the maximum response of drug C is significantly lower while reaching the minimum desired level, right? So it's reached this right here, right? But it stays below the max. So you could say pretty confidently that drug C is the safest to administer. All right. So that's it on 4.7. Stay tuned for 4.8. And I hope you guys are all doing okay. Just text me, or text me is best, but you can email me if you'd rather, if you're having any concerns or questions, or will need to meet with me. I'm thinking that I will be available first thing Thursday morning next week for individual consultations, but hopefully this video will help you. You can print out the notes and just follow along and stop the video when you need to. All right, I hope everybody's well. Thank you.